Welcome to your deep dive. Sounds like you're ready for some really big mysteries.
Yeah.
We're going from tiny particles all the way out to the vast expanse of dark matter and energy.
Yeah, and maybe find some unexpected connections between them.
Exactly. Get ready to stretch those brains, though. It's going to be a fun ride.
Definitely fun. These concepts, they can be mind-bending, but they really do start to show us how the universe works.
Okay, let's start by shrinking ourselves down. Way, way down.
Okay.
Imagine a world that's only in two dimensions, like a flat sheet of paper.
Right.
Now, if there was a creature, let's call her Dottie, living in this 2D world, how would she even perceive a 3D object?
That's a classic thought
It's
experiment.
like a sphere, for example, passing through her world.
It really shows us how limited our perception can be.
Right.
So Dottie, she'd only see the sphere as it intersects with her 2D plane.
Oh, okay.
So she'd see a point appear, then grow into a circle, then shrink back to a point as the sphere moves through.
Oh,
To her, it'd just be these disconnected events, almost like magic.
yeah, be like, what is going on?
Yeah,
And here's the crazy part. We're basically like Dottie, but in 3D. What if there are higher dimensions that we can't see?
right.
Could we be interacting with objects from those dimensions without even realizing it, just seeing slices of their reality?
Hmm. That's where the idea of wave-particle duality gets really interesting. I'm sure you've heard that light can act like a wave,
Hmm.
spreading out like ripples.
Uh-huh.
But it can also act like a particle, a photon, like a little packet of energy.
Right, I've heard of that.
So what if this isn't light changing its nature, but rather us seeing different aspects of a 4D structure?
Whoa, wait. You saying that like an electron or a photon could actually be a 4D object, and we're only seeing 3D slices of it?
Exactly. Maybe an electron isn't switching between being a wave and a particle,
Yeah.
but rather just revealing different parts of its 4D self depending on how we observe it.
Okay, so like how Dottie only saw circles when the sphere passed through her 2D world.
Exactly. It's pretty mind-blowing, isn't it?
Yeah, but if we're stuck in our 3D world, how can we even begin to understand something that's 4D?
Well, that's where math comes in. It's our most powerful tool. We can use mathematical equations to describe and model things we can't directly see.
Right. Equations can help us make sense of the unseen.
Exactly.
So about light, it's an electromagnetic wave,
Yeah,
but it's not affected by electric or magnetic fields like electrons are, right?
that's right. Kind of counterintuitive, but light is influenced by gravity.
Oh, interesting. So when light passes near a massive object, like a star, its path gets bent.
Exactly. It's called gravitational lensing.
Gravitational lensing. So light is really interacting with the universe, mainly through space-time itself.
Yeah, almost like it's woven into the fabric of the universe, not just moving through it.
That's wild.
It is.
Makes you think about Einstein's famous equation, EMC4Z. If mass and energy are interchangeable, how does mass actually warp space-time to create what we experience as gravity?
Okay, imagine a bowling ball on a trampoline.
Got it.
Creates a dip,
Yeah.
right? Similarly, large mass in space-time creates a curvature. And that curvature is what we experience as gravity. Objects aren't actually being pulled towards Earth. They're following that curved path created by Earth's mass.
So it's all about geometry.
Yes, it is.
Okay, so mass warps space-time, and that's what we feel is gravity. But what about objects that aren't moving? They still have mass, so they're still warping space-time, right?
Right.
What keeps them from just collapsing in on themselves?
Well, that's where inertia comes in. Think of mass as trapped energy within space-time.
Trapped energy.
Yeah, and this trapped energy creates resistance to movement. That's what we call inertia.
Inertia.
And the more mass an object has, the more energy is trapped, the harder it is to move.
So mass is both warping space-time and resisting movement within that warped space-time.
Exactly. It's a dynamic relationship. Mass creates the curvature, and the curvature influences how mass moves.
Wow. A cosmic dance between mass, energy, and space-time.
It is, yeah. They're all intertwined, influencing each other, this incredible interplay.
And to think, that's just the tip of the iceberg. We haven't even touched on dark matter and dark energy.
Right, and that's the vast majority of the universe.
Amazing.
Remember everything we can see, stars, planets, galaxies, all the stuff made of atoms.
Yeah.
That's only like 5% of the universe's total mass and energy.
Wow.
The rest, well, it's this mysterious stuff.
Dark matter and dark energy.
Exactly.
Let's start with dark matter. It's invisible, right? So how do we even know it's there?
We can't see it directly, but we can see how it affects things through its gravity. Galaxies are spinning way faster than they should be if we only look at the matter we can see.
Huh. So, like, it's holding them together?
Yeah, it's like an invisible scaffolding. Holding these huge cosmic structures together prevents them from flying apart.
Wow, so there's this invisible stuff out there, and it's got a gravitational pull.
Right. Keeps those galaxies spinning at the speed they do.
Okay, so what could this dark matter actually be?
Million-dollar question. One idea is that it's made up of massive particles that just don't interact with light. That's why we can't see them.
Oh, I see.
These hypothetical particles, they're called WIMPs.
WIMPs.
Yeah, weakly interacting massive particles.
WIMPs. I love it. But if they don't interact with light, how could we ever actually detect them?
Well, scientists are looking for tiny, tiny interactions, like if a WIMP bumped into an atomic nucleus,
Oh.
which could release a tiny amount of energy, and we could maybe detect that.
Such a tough job.
It's like trying to hear a whisper in a hurricane.
Wow. Okay, you mentioned earlier another possibility, right? Like dark matter existing in higher dimensions.
Yeah. Now, that's a mind-bending idea,
Yeah.
but definitely intriguing. Imagine if dark matter exists in a dimension we can't see directly. It might be casting a kind of, well, gravitational shadow in our 3D world.
Oh, I see. And that's what we detect as its gravitational influence.
Exactly.
So we've got dark matter holding galaxies together. What about dark energy? What's its role in all this? Dark energy is even more mysterious. We know the universe is expanding. But it's not just expanding, it's accelerating.
Whoa, so something is pushing everything further apart. That's dark energy.
Yeah. Something is pushing it all apart. And we call that something dark energy.
So dark matter is like the glue, holding things together, and dark energy is the engine, driving everything apart.
Good analogy.
What are some of the leading theories about what dark energy could be?
One possibility is something called the cosmological constant.
Okay.
It was actually proposed by Einstein way back when.
Oh, wow.
It's basically a property of space itself, like a built-in energy that creates a repulsive force, pushing everything apart.
So, like, empty space isn't really empty.
That's the idea.
It's got this inherent energy, and that's what's driving the expansion.
Could be. Another idea is something called quantum vacuum energy. Even in a perfect vacuum, at the quantum level, there are these tiny, tiny fluctuations of energy popping in and out of existence.
Oh, wow.
So empty space is actually teeming with all these virtual particles.
So that energy from all those virtual particles, could that be contributing to the expansion of the universe?
Exactly. And that's what makes this all so fascinating. It's still a really active area of research. Scientists are working hard to understand dark energy and its role in all of this.
It's incredible to think about. 95% of the universe is made up of these things we barely understand. Do you think dark matter and dark energy could be connected somehow?
That's a great question. A lot of physicists are working on that. Could they be different aspects of the same underlying thing?
Right.
Could they be interacting in ways we don't even know about yet?
It makes me wonder if all these ideas we've been talking about, duality, dimensions, mass, energy, dark matter, dark energy, are they actually all connected?
Like different parts of the same puzzle.
Yeah, a single fundamental principle that governs everything.
That's a profound thought. And it leads right to the ultimate goal of physics. A unified theory that can explain it all. A theory of everything that could describe all the forces, all the particles, from the smallest quantum fluctuation to the largest structure.
We talked about it earlier, but it's worth coming back to. How can math help us unlock these mysteries, especially since we can't even directly observe them?
Math is like a language.
Mm.
It lets us describe and model the universe, even the things we can't see.
Right.
We use equations to make predictions and test them against what we observe. It helps us refine our understanding of how things work.
So those equations we talked about earlier, the wave equation, Schrodinger's equation, Einstein's field equations, could there be like a super equation?
A super equation.
Yeah, one that encompasses all these ideas, a mathematical framework that could describe the whole universe.
That's the dream. And while we're not quite there yet, there's some really cool research going on, like string theory and quantum gravity. They're pushing the boundaries of our mathematical understanding.
Let's dive into those a bit. String theory. That sounds kind of sci-fi, to be honest. What's the basic idea?
The core idea is that the fundamental building blocks of the universe, they're not actually point-like particles, but tiny vibrating strings. Yeah, and the different ways these strings vibrate, that would give rise to all the different particles and forces we see.
Oh, I see. So it's like a cosmic symphony
Yeah,
with different notes creating all the diversity we see.
exactly. And one of the coolest things about string theory is that it needs extra dimensions to work. Mathematically, that is.
Extra dimensions.
Yeah, we experience 3 dimensions of space, 1 of time. But string theory says there could be 6 or 7 more spatial dimensions, curled up super tiny.
Whoa. Okay, so are these extra dimensions like parallel universes or something?
Not exactly. They're more like extra directions, but curled up so tightly that we can't experience them. Think about a garden hose.
Okay.
From far away, it just looks like a line, 1 dimension. But if you zoom in close, you see that 2nd dimension, the circle.
So these extra dimensions, they're all around us.
Yeah.
Just too small to see.
That's the idea. And these extra dimensions, they could be where some of the mysteries of the universe are hiding. Maybe even dark matter and dark energy.
Fascinating. What about quantum gravity? How does that fit in?
Quantum gravity, that's the big quest to find a theory that can unite general relativity and quantum mechanics.
But don't those two theories kind of clash? Like at a fundamental level?
They do. That's the whole problem. At really, really tiny scales, where quantum effects are dominant, our understanding of gravity just breaks down. And that's a big problem because those tiny scales, well, that's where the universe began, in the Big Bang.
Right.
So to really understand how it all began, we need a theory that bridges the gap between gravity and quantum mechanics.
So we're missing some pieces of the puzzle.
Yeah, we're trying to put it together, but we're missing some key pieces.
Do you think we'll ever find those pieces? Like, will we ever unlock all the secrets of the universe?
I'm optimistic. We've come so far in understanding the universe, but there's still so much more to learn.
Yeah.
And the more we learn, the more we realize how much more there is to know. That's what makes it so exciting.
It really is mind-blowing. All these things we don't know, and the things we don't even know we don't know. But before we go too far down that rabbit hole, I want to touch on one more thing. The multiverse.
Ooh, okay.
Is there any real science behind this idea that our universe might be just one of many?
The multiverse, it's one of those ideas that, well, it pushes the limits of what we can observe and test right now, but it's a real possibility.
Really, it's not just science fiction.
It comes up in some of our most successful theories.
So where does the idea even come from?
Well, one path leads from cosmology and the theory of cosmic inflation.
Okay.
That theory says that in the very first fraction of a second after the Big Bang, the universe expanded insanely fast. And some versions of that theory, they predict that this process could have created multiple bubble universes.
Bubble universes.
Yeah, all expanding and evolving on their own.
Whoa, so our universe might be just one bubble in a whole foam of universes.
Exactly.
That's wild. Are there other hints that this multiverse might actually be real?
Another path comes from string theory. Remember all those extra dimensions?
Yeah.
Well, string theory allows for a huge, huge number of possible universes, each with its own unique set of string vibrations, and that means different physical laws.
So like every universe would have its own unique set of physical laws.
Yeah, like a cosmic lottery with different winning numbers. And we just happen to be in the one where the laws are right for us.
Wow. That's humbling, to say the least. So some physicists believe that this could explain why our universe seems so perfectly tuned for life.
Yeah, exactly. If there are tons of other universes out there, it's not so surprising that we find ourselves in one that works for us.
It's fascinating, but also kind of unsettling. If all these other universes are out there, what would they be like?
Right.
I mean, could the laws of physics be totally different? Could gravity repel instead of attract?
Or time could flow backward.
Exactly. It's mind-blowing. But I guess we can't just, like, hop in a spaceship and visit these other universes, can we?
Not with our current understanding of physics, no.
Too bad. But even if we never find absolute proof that the multiverse exists, just thinking about it changes our perspective, doesn't it?
For sure. It reminds us that we're always learning and our understanding of the universe is constantly evolving.
Absolutely. Well, we've covered a lot in this deep dive. Dimensions, duality, dark matter, dark energy. We even touched on the multiverse.
It's been a journey.
My brain is definitely full. Feels like we've only just scratched the surface.
There's always more to explore.
That's the beauty of it.
Yeah.
So for our listener who's now super curious about all this, what advice would you give them? Where should they go from here?
Just stay curious.
Yeah,
Don't be afraid to ask questions. Explore the things that fascinate you.
right. Dive deeper.
There are so many resources out there, books, documentaries. You can even find online courses.
And honestly, just talking to people who share your interests is a great way to learn.
Exactly. And don't worry if you don't understand everything right away. These are big ideas. Even the smartest people in the world are still working on them.
That's right. The journey is just as important as the destination. Embrace the mystery.
Enjoy the ride. The universe is full of surprises. Who knows what we'll discover next?
Thanks for joining us on this deep dive. Keep that curiosity burning bright. And we'll see you next time for another adventure into the wonders of the universe.